All right, a slight break from the potentials and more work on how the actual vector potential and current density relate to the magnetic field. So here we want to prove the following uniqueness theorem. If the current density J is specified throughout a volume V, and either the potential A or the magnetic field B is specified on the surface S bounding the volume V, then the magnetic field itself is uniquely determined throughout the volume V. This is pretty cool sounding, so let's see if we can find out how to approach it. So we were given a hint in the problem, and it says first use the divergence theorem to show that this expression holds for some arbitrary functions of u and v. So let's apply the divergence theorem to the function u cross the curl of v, noting that the product rule. And if you note, this is kind of how we set up for the magnetic field cross magnetic field, given that v is something like a. But nonetheless, apply the divergence to this product, and we get this nasty product expansion. So we can further simplify this down, rather not even simplify, but we can substitute this into the integrals, and we can see that we do indeed get the expression that was given in the hint from the divergence theorem, which relates the volume to the surface area. Good to go there. All right, but now, as always, let's suppose that there are two unique solutions, B1 and therefore A1, and B2 and therefore A2. And if we define B3 to be the difference between B2 to B1 and A3 the difference between A2 to A1, so that the curl of A3 equals the magnetic field B3, and we know that the curl of B3 gives us the curl of B1 minus the curl of B2, thus mu naught J minus mu naught J gives us 0. That's good to see. And so we set UV equal to A3 and substitute in. All right, sure enough, we substitute in. Fair enough. We know that all the curls of A3 give us the field B3. All right, but we just showed that by taking the curl of B3 and getting the current density, that equals 0. So that cancels to 0 in the second line of the integrals. And we can see that the dot product just yields the magnitude squared, again, all over the volume d tau. But that's equal to some surface area, right? Or some surface integral, rather. So we take A3 times the curl of A3, but we know that the curl of A3 is B3, so we get A3 cross B3. But they tell us that either A is specified, in which case A3 is 0, or B is specified, in which case B3 is 0 at the surface. In either case, we see that surface integral ends up going to 0 because of the cross product, and we're left with B3, the integral of B3 squared d tau equals 0. And if that's true, then we know that B1 has to be equal to B2. Fair enough. Nice to see that come together too.